every lesson we've ever done on YouTube.
You have missed a couple lessons though.
I was gone for 2 days.
No, I mean on the YouTube channel.
Okay.
So you go to, yeah. It's on Google Classroom. The link's on Google Classroom. You go right to it. Okay, so yesterday we filled out the table. We calculated the chi-square. For each individual color had a chi-square. So the total chi-square was 26.1353. Okay. And then we kind of went backwards as to what we did there. Conditions, we got stuck on the SRS. It was not done correctly. So we want to note that. We want to note that the SRS was not done correctly because it was a convenience sample, right? We talked about the correct way to do it, but this was done in an incorrect manner. So we just note it, keep going. Okay. Let's see. Why is that not in here? Okay. So the second condition is independent. So that one, how do we check that one? All expected counts are at least 5. So we're going to go to our table and make sure that all expected counts are at least 5. Okay. So nothing's too small. And it looks like every single one of our 6 is above 5. Okay. So number 2 says all expected counts greater than or equal to 5. Yes, so we say yes. 6 out of 6 equals 100% of them are above 5. Okay, that's the second one. The last one says large counts. 80% of our expected counts are at least 1. 80% of them are at least 1. Okay. So we say 80% of expected counts are at least 1, greater than or equal to 1. And yeah, if they're all above 5, if they're all at least 5, then they're all 80% of them are going to be there. So we say yes, 6 out of 6 equals 100%. So we still have 3, and they cover the same thing. One's randomization, one's what do they call it? Not the 10%, independence, which is the 10%. That's why we do the 10% condition for independence. And then the large one is large. The last one is large counts, which is for normality. They're just different. Okay. For chi-square. This is only for chi-square. Everything else uses the same ones we've been using since chapter 7. Okay. Okay, so we've done population parameter, hypotheses, significance level. We did conditions. So 1, 2, 3, 4. We did calculations. We're missing a couple. First one we're missing is test statistic. We're kind of going backwards on the first question just because it was easier to do it that way. Okay, which equations did we use? Which equations did we use to do the calculations? Chi-squared. That's why it's called chi-squared. Equals sigma observed minus expected squared over expected. Okay. Degrees of freedom. How do we find degrees of freedom?
N minus 1.
Not n minus 1, because n doesn't mean anything on this question. What was it? Because we didn't have an n on this one. How do we calculate degrees of freedom?
The category.
Categories minus 1. Yep, categories minus 1. Okay. So degrees of freedom, in this one, we had 6 different categories. So on this guy here, we would have 6 minus 1. We'd have 5 degrees of freedom. Okay. All right. Test statistic, we're done. The last one we have not covered, I believe, is conclusion. I don't know why I didn't include this. There's a couple slides I'm missing. I don't know why they didn't come out, but let me show you. Let's see here. Okay, so you have this slide, 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 this one. Oh, that's why. So we did this slide right here, conclusion. It's the same conclusion as before. P-value versus alpha level. Reject or fail to reject the null hypothesis. Therefore, we have sufficient evidence, or therefore we lack sufficient evidence. So it's nothing new. Okay. So what are we missing? Can we do our conclusion right now? We don't have the p-value. We do not have the p-value. So to find the p-value, we're going to have to go to our tables. So go to your tables, and I'll show you how to interpret. That means take out your tables. Okay, so you're going to go to this side here. This side of the table is here. So we have T, we've used T. We use that plenty. Now we're going to use the one that's skew. Chi square. You can notice this guy right here. Chi square. Okay. So chi square is not normal. Chi square is skewed to the right. Unlike T and Z, it is skewed to the right. Okay. So how do you read this table? Well, first of all, you start with degrees of freedom. So how many degrees of freedom did we have on this last question? 5. So we're going to focus on this row right here. Okay. Now we have to go find each of those is a chi square. Each of these guys right here, each of these guys in a row that I highlighted in blue are a chi square. We have to find where our chi square is. So where would our chi square fit on that? Picture it's a number line. Picture this is a number line here. Because it is, they get bigger. It would be where though? Where would it be? Like over here? So where would it be? You say it's off, so would it be on this side over here? Like if this was a number line here, and it's not on the number line, would it be like over here? Where would it be? To the right. It would be off the graph, off the number line to the right. Okay. So, and then each of these guys, if you go straight to the top, each of these guys, if you go straight to the top, they each have a decimal at the top. That's the probability. That's the p-value there. Okay. So if I were to have, let's say, my chi-square was exactly 16.75, my p-value would be 0.0050. If my chi-square was 11.07, the p-value would be 0.05. Well, let's say I have a chi-square in between those. So let's say my chi-square was 13.01. That's in between here, right? So that means your p-value is going to be in between here. So it's going to be between 2% and 2.5%. That's as close as we can get. Okay, so knowing that, what percent or what probability is ours going to be? Smaller than this guy here, yeah. Smaller than this guy here. Because you can see the numbers go up in value, the probabilities go down in value. Okay? So it's going to be less than this. Okay, so let's go write that down. We write it down with our calculations because p-value is a part of the calculations. So we say is less than 0.0005. I'm not going to say equal to, it's less than. Okay, so it's less than 0.0005. Now they didn't give us a number. Is that enough to say we can reject or fail to reject? Yeah, it's enough. That's right. That's all we need in our conclusion. We just need enough to say fail to reject or reject. Okay, so there's our p-value. Okay, so let's go down to the conclusion. Since p-value less than 0.0005, okay. Let's see, let me try to get these on the same. Okay, since our p-value is less than, so we can say is less than. I would probably say is less than since I already used, I don't want to use double symbols. Is less than alpha, not a, alpha 0.05. Anytime the p-value is less than alpha, what do? We reject the null hypothesis. Okay. Therefore, we have sufficient evidence to show or to suggest that, how do we put the alternative in? So what would we say? So we have, therefore, we have sufficient evidence to show, yes, there we go, to show that the distribution of colors is not as the company claims. Okay, done. Okay. All right, so we have conclusion, test statistics, conditions, significance level, hypothesis, population. Yep, we got everything. All right. Okay. All right, so that's, remember I told you guys at the beginning of yesterday that there are two types of goodness of fit. So these are just goodness of fit. There's two other types of chi-square, which we'll talk about later this week. One of them was, so one of two, right here. There are two types. Which type was the one we just did? I've heard both answers, so I'm not going to say which one. Which one? Which one was the one? The one we just did right now. The one we just finished 10 seconds ago. Which one was it? Was it equal proportions, where all the proportions are expected to be the same? Or was it a fixed or given proportions, where proportions are expected to follow given values or given expectations? So it's easy to check, because this guy right here says all proportions are expected to be the same. Go to your table. Are all proportions exactly the same? No, 24%, 20%, 16%, 14%, 30. Yep, so that one's not that one. So we've done this one already. The last problem that we have is going to be an example of number one. Okay, so now we're going to do an equal proportions. Okay. Okay, so now the last problem. So we have counts of 256 randomly selected executives in 12 astrological zodiac sign categories. So have you guys heard of the zodiac signs? Okay, you guys have had some familiar with it. It deals with astrology. Okay. Yeah. Mm-hmm. So the natural null hypothesis is that birth dates of executives are divided equally, so it doesn't matter. So they're trying to say, does it matter? Are all executives equally distributed between the 12 signs, 12 astrological signs? So pretty much, you just, when are they born? Are they born? They want to know, are executives born during a certain time more likely than others, or are they born just kind of, does it not matter, right? That's what we're going to test. The test statistic looks at how closely the observed data match this. So it should be match. That should be match this idealized situation. Are zodiac signs of CEOs distributed uniformly? What does uniformly mean? All the same, right? People who wear uniforms, they all dress the same. Uniformly, right? So uniform, they're going to use that word a lot. So when they use that word, that means chi-square, goodness of fit, equal proportions. Sometimes they might just say, are they the same, or distributed similarly, distributed the same? Obviously we know what it's going to be because it's in the notes, but I'm talking about when you see it on an FRQ, are you going to know this is a goodness of fit test? Okay, because that's the key there. Looking at some of your tests, on the multiple choice, I think some of you were confused as to which kind of test to use because there were some that were off. Okay, so I just want to make sure, what are we looking for here? So this is a big word here. Do this data. This is the observed. So there were 23 executives who are Aries. Aries means they were born from March 21st to April 19th. So right now, they were born from April 21st to March 21st to April 19th. 23 were. Taurus, if you were born from April 20th to May 20th, you are considered a Taurus, so on and so forth, right? Okay. All right. So 23 of them are considered Aries, 20 of them are considered Taurus, 18 Gemini, 23 Cancer, and so on and so forth, right? Okay. So if we were doing, so let's do calculations like we did first. Let's do calculations first, since we have the table already set. Sometimes they won't give you a table. This time they did give you a table. Okay, so let's do our calculations right now. We know it's chi-square. We know it's goodness of fit. So expected counts. What are the expected counts going to be? How do we find expected counts? There you go. If they're evenly distributed, uniformly distributed, the same distribution, that means everyone should be the same, right? So each one of these 12, we should expect how many? 21.33. So let's go 21.33 for all of them. Okay. We didn't have to calculate anything, or you just calculated divided, right? You just divided. So this one's different. This one is different than how we calculated this table here. This table here was calculated a different method for expected counts, right? So it just depends on which one it is. They're both goodness of fit tests, but they have different way of calculating expected values. So just be careful there. Okay. All right. So calculations. So now we're going to do chi-square. This one has more. So I'm going to show you the calculator. We'll do this one using the calculator. Okay. More so than we did the first one. Okay. So, chi-square says, so to calculate chi-square, what we're going to do is we're going to find the summation of observed minus expected squared over expected, right? We're going to do that for each one of the 12. Each one of the 12. So the first one would be 23 minus 21.33 squared divided by 21.33. Okay, so this is what we're going to do. This is the work we're going to show. And then we'll go to the calculator. So I'm going to show the first two, how the first two are calculated. So the one I just did. The one I just did. 23 minus 21.33 squared divided by 21.33. Plus the next one. The next one would be Taurus. For Taurus, it's 20 minus 21.33 squared over 21.33. Plus dots, dots, dots. Continues on with that one, and then I would do the last one, which was Pisces. Pisces is 29 minus 21.33 squared over 21.33. Okay, that's all the work we need to show. The rest of it, we're going to use the calculator. I'll show you how to use the calculator on this one. Okay, so we're going to calculate our chi-square statistic for all of them and add them up. Okay, so let's go to the calculator. Okay, so when we go to the calculator, first thing we're going to have to do is we're going to have to make lists. One is observed, one is expected. So let's go make a list. So 23, 2018. 23, 2019. Okay. So there's a fast way of doing that. You can do it. You can do it the same way, but there's also a faster way of doing it. Say enter all of these values here. I want you to go 256 divided by 12. Oops, why won't let me do that? Let's see. What did I do wrong? $256. Oh, maybe I need to put divided by in here. Divided by. Nope, I guess not. There was a way to do it, but I guess for some reason I'm not doing the right thing. So 21.33. There's a way to cut and paste in too, but I just don't know how. There's ways to do it. I don't really use that a lot, so I just don't know how to do that. I haven't looked it up. Okay. So we're going to create a new list. We're going to create a third list. When you want to create a new list, you got to go to the top, highlight the list, hit enter, and then you should have a blinking cursor at the bottom. So how do we calculate chi-square? Okay. So how do I use it? I'm using my list. Okay, so I'm going to do that. Parentheses, L1, that's observed, minus expected, L2, squared, divided by L2. Hit enter, and there's your chi-squareds. Okay. So it'll calculate them all in one big shot. Now, how do I get my total chi-square? Because each one of those represents chi-squared for each one, right? So how do I get my total chi-square? One var stats. So we go one var stats for L3. Nope, not L2. L3. Oops, no. Yeah. Let's see here. Clear. L3. So the one with the sigma, there's two of them with sigma. One with sigma squared, x squared, and one with regular sigma. I already squared them. That's what the formula did. So the one I'm looking for is the one without the square. 9, 4, 6. Okay. All right.
So we're going for the one without the square.
Okay. I already squared them, so I don't want to square them again. Okay. Now, that's just a faster way of doing it. You don't need to do it that way, but it's just a faster way of calculating chi-square for each of them, especially when there's a long list of them, and then adding them all together real fast. But you do not need to do that. I find a lot of people say, I don't have a calculator. Like, no, you don't need to do that. You just do each one of them individually. It'll take you another 5 minutes. But what's 5 minutes to get an A, right? Okay. You can calculate. You literally can use a dollar store calculator to do that problem right there. And then you just do that for all the rest of the 12. Add them together, and you'll eventually get that. Okay. But it's just since we have these calculators, I use them. Okay. All right. Degrees of freedom. Degrees of freedom. What are we going to have for degrees of freedom here? 12 categories minus 1. If it's calculations, we have to show how we got the calculations. Okay. P-value. P-value. Since this is calculations, we also need p-value. So we go to 11. It's going to be on the left, on the extreme left. Right? It's lower than the extreme left, the last one that's extreme. So it's going to be even lower than this. A lower chi-square means a higher probability, though. So it's going to be greater than 25%. All right, so let's put greater than 25. Okay, there's the p-value. Okay. All right, so that's all calculations. So let's go on and let's fill in the rest of the holes that we skipped on their way here. So population parameter. You got a lot of proportions. Just like the last one, we had 6 proportions. How many proportions are we going to have? We had 6 proportions, 1 for each color. How many proportions are we going to have here? 12, 1 for each sign. Okay. So we don't have to list them all. We just have to be general with how we label them. Okay. So let's see here. So yeah, so we don't have to list them all. You could just go the first 2 AT ... The last one is Pisces. True proportion of what? True proportion of, that's for 1. Like if I was doing just for Aries, that would work. But I'm not doing it just for Aries. I'm doing everyone together. So what do I have to put? What word do I have to put in there to show that I'm doing everyone together in one swoop? No. If only we did a problem like this before. No.
Every month?
No.
All months? Yearly?
No.
Oh,
See, the way you guys are thinking, we would have just for 1. Right? I don't want to do 1. I want to do them all together. I want to look at all of these numbers together. Missing something. What are you looking at here?
All of the months.
I think someone said it.
Was it hard stuff?
I think I heard the word.
Each? He said each.
Nope.
All?
I think I heard the word somewhere, but no. Do I really have to scroll back? You guys have it. Well, you should have it. Oh, we don't have it. Don't have it there. I should have had it there. Okay. True proportion of distributions for. I'm not looking at just one number. I'm looking at many numbers for many things. So if it's many numbers for many things, we always want to use the word distributions. Okay. Otherwise, we just think it's one number. Okay. That's the word we want to use. Distributions. Distributions of what? It's right here. Distributions of. It's not about the month. What's the question asking? Their sign, right? Distribution of zodiac signs for CEOs. Right? In practical terms, it is the month. It is the time of the year that counts, right? But that's not the question. The question is referring to the zodiac sign. So we want to make sure we include that. Okay. Next is hypotheses. We have the null and the alternative. Okay.
Doesn't the prompt say the null hypothesis?
What?
Isn't the natural null hypothesis?
No.
That's not it?
No.
What is it? City distribution.
What's wrong with the one I have right here? It has no context, yeah. Automatic strike right there. So make sure you put it in context. So how can I put it in context?
The stated distribution of zodiac signs for CEO is
there you go. Okay. The stated distribution of zodiac signs for CEOs is uniform. Okay. What's the alternative? There you go. The stated distribution of zodiac signs for CEOs is not uniform. You can rewrite it. Okay, you can rewrite it if you want, or you can use the quotations if you want. Okay. All right, significance level alpha equals in say, so we'll just use 5%. Okay. And then we're missing, we already did calculations already. Conditions, so let's do conditions. Okay. SRS. Stated. What was stated?
We have counts of 256 randomly selected executives.
So again, what was stated? I'm not asking you to read it. I'm telling you to tell me what. No. What's stated?
How they were randomly selected.
Not. Did they tell you how they randomly picked them? No, they didn't. Why? What is stated though? There you go. That there was a randomization to select CEOs. Okay. Number 2. All expected counts are greater than or equal to 5. So we go back to our table. Yep, they're all the same. Since this is uniform, they're all the same and they're all above 5. So 12 out of 12. Yes. 12 out of 12 equals 100%. Okay, and then the last condition, 80% of expected counts are greater than 1. Huh?
So why does the third condition exist if the second one already?
Exactly. I was waiting for someone to say that. Actually, I said that yesterday, but no one brought it up, so I kept doing the third condition.
It's actually the same thing.
Exactly. So if you know that, we don't even have to do this guy, right?
Are they still gonna check for it?
No, because you already did it. It's redundancy. But I kept doing it because no one brought it up. I had mentioned it yesterday, but no one brought it up, so I kept doing it. But yep, if you notice that, it's redundant. Because if all of them are 5 or greater, then of course 80% of them are going to be above 5 or above 1.
Nice. If you don't meet the second one, do you have to do the third one?
Yes.
Yeah, that's true. If you get the second one, the third one, right?
So there you go.
Not necessarily the third one.
If you don't remember that, just do all 3 of them. It doesn't hurt you to do all 3 of them. Won't take any points off to do all 3 of them. Just the way I did it for the first one, nothing bad will happen. Okay. Test statistic. Okay. So we already did all of this, but which test statistic do we use? Well, it's chi-square. So any chi-square test is going to use chi-square test statistic, which is given. Other side. Very bottom. Okay. And then degrees of freedom we also used. Categories -1. And then the last one is conclusion. Okay. Since on that one. P-value, which was greater than 0.25, is greater than alpha, which is 0.05, we failed to reject the null hypothesis. Okay. Therefore, we have sufficient or significant evidence. Yes, you're right. We do not have, or we lack, to suggest or to show what?
What the distribution of zodiac signs for CL is uniform?
There you go.
Or not uniform?
Is not uniform. Good. To show that the distribution of zodiac signs for CEOs is not uniform. Okay.
What would we put for the first sentence if it is between two numbers?
Okay, good question. So let's say I have two answers to that. I'll show you the first answer. Let's say it's between, let's say we had a right here, right? Let's say we had one right here, which is between this guy and this guy, right? 0.05 and 0.025. So let's go back.
So you could fail. There's a chance of fail to reject.
Okay, so where is it? So first of all, we'd say 0.05 p. We can say p value.
Greater than.
So in between there, right? We'd say that instead. Would we reject or fail to reject this guy? Can't do both. So let's say I had this one instead of
Oh, you failed to reject.
this guy. Oops, no. Instead of this guy here. Would we reject or would we fail to reject? We would reject. Why reject?
Oh, right.
It's going to be smaller than 0.05 because there is no equal sign here. There's no equal sign, right? For it to be exactly 0.05, it has to be exactly this guy here. We didn't say it. We said it was between these two guys, right? So if it's not this guy exactly, if it's in between them, that means it's in between. It's not. Okay? Yeah. The second way, I'm going to show you the second way. The second way is using your calculator. So go to, let's see, go to your calculator. You got everything in L1 and L2. So you're good there. Go to tests, the list of tests and intervals that we usually have. There you go. So you're going to go all the way to the bottom. There's two, right? There's two chi-square tests. Yeah, there's one that says chi-square tests, and there's one that says chi-square GOF or GOF test. What do you think GOF stands for? Goodness of fit. So we're going to use that one. Observed, where's our observed? Where's our expected? How many degrees of freedom do we have? I'm going to do draw just to show you, because remember chi-square is skewed. With chi-square, you always shade to the right. You always shade to the right. So here is our chi-square, 5.0946 right here, and then they always shade to the right if you're doing chi-square. Okay? That's a big portion, right? That's a big portion. So that's why our p-value was a lot bigger than 25%.
Will the p-value and the alpha level be equal to each other?
No. If the p-value and the alpha level are exactly equal, I've never seen that ever. Because that's how we determine if we reject or fail to reject. So they'll be close sometimes, but they'll never be exactly. Okay. All right, so that's goodness of fits. So the assignment, it's from your book. It's from 11.1. Okay, so tomorrow we're going to start on 11.2. 11.2 is 2 tests. There are 2 chi-square tests. One of them is homogeneity of populations, and the other one is test for independence or association. Okay, they're very similar. They're very similar, and they're done exactly the same way, but they're just for 2 different things. Okay, we'll talk about it tomorrow. Okay.
Okay, so why don't we do these tests?